The way this is going to be structured is we're going to start by looking at why I'm even exploring this topic, why is this important, and who is even asking this question. Secondly, I'd like to do of the short overview of the context in which this happens, which components in Kafka are impacted by this choice, where does it matter. Then, on this foundation, we will look at the available options and then find out how these options compare to each other, and finally conclude with some recommendations. To explain where the question is coming from, I'd like to speak a little bit about my work at Confluent. I've been with Confluent since 2021 as a solutions engineer, which means that I am part of the account team of specific customers. My role is a technical one, and my goal is to help customers find the best solutions for their technical challenges. So sometimes this means figuring out some configuration, sometimes finding the right architecture, and sometimes deciding which data format is the right one. And I've received quite a few questions about the data format from a few different customers, and I found it really interesting that this question came up in very different situations. The most obvious scenario where this question can come up is when Kafka is newly introduced. There are a lot of choices to make in this situation, many features to test, and naturally the choice of data format would also come up. But interestingly enough, this is not the situation where this question shows up most often. And I think this is because in this situation, there's one team driving the adoption of Kafka. This team has an existing stack. They have studied the documentation. They decided on a data format to fit that stack. And since most often it's only one team, there's nobody to disagree with, no competing preferences, no competing priorities. It's still important to think about this looking into the future, but more often than not, there's just an obvious answer to this, and it's fine. Most of the times, I hear this question when there's a central team, like a platform team or an operations team, which wants to implement some standards. They work with multiple development teams, and some of these development teams are newer and ask for guidance, others run into various issues, and more often than not, these issues cost the central team a lot of time. And as the adoption of Kafka grows within their enterprise, more and more issues occur, and the platform team cannot scale linearly with the number of issues. So naturally, they're looking for a standard. And they want to find a standard with which everyone is happy, that respects the preferences of the different development teams. But sometimes these preferences might be competing with each other. Otherwise, there are new business initiatives like data mesh, data products, which depend on the ability to collaborate more effectively, and it helps if you have a standardized format here too. And then there's even a more challenging situation, which is the situation of unforeseen collaborations, like two companies which merged. And the effort of different teams with different technology stacks needs to be aligned, and more often than not, there are competing priorities of what should be done first. So maybe to look at where this fits in, let's do a quick recap on how Kafka works and why and when a data format is relevant. So we have messages, which are the unit of data, the producers, which write messages to Kafka, and the consumers, which read them. The producers and consumers read and write independently of each other, and each message is appended to the log and assigned an offset. The message may have a key and must have a value. So in this presentation, we're focusing on the value of these messages. But by default, the messages are just byte arrays to Kafka, so there's no format and no meaning attached to them. But this also means that messages cannot be easily understood. So to truly decouple consuming, to give the consumer a way to find out how to understand the message, there must be a way to tell this consumer how to handle any changes which have happened on producer side. So to remove this need to coordinate producers and consumers, it is recommended to introduce schemas. A schema imposes a structure on the message value, and this way makes sure that the message can be easily understood. It is recommended to use well-defined schemas and some common repository to store them. Confluent Schema Registry is such a centralized repository for managing and validating schemas used in data processing and serialization into and out of the binary format. So what happens when you introduce Schema Registry? A few additional components are prepended by the serializer to the wire format. The first one is the magic byte, which stands for the Confluent serialization format version number, which is then followed by the schema ID and then the data. So then, even a consumer who is uncoordinated with a producer and would not have known how to read the data can get the schema from the schema registry using the schema ID provided in the data and find out what the message means. So how does this work? We have the producer and the consumer who each have a local cache and the schema registry. When the producer wants to register a new schema, it sends the schema to the schema registry and gets back the schema ID and will store this in the local cache. The producer adds the schema ID to the message and sends it to the Kafka cluster. The consumer reads the message from the topic and checks if it has the schema for the provided schema ID in its local cache. And if it doesn't, it calls the schema registry with the schema ID and gets the schema back. The schema is then stored in the local cache. So if we complete this diagram by also adding the partition, the topic, and the cluster, we have the full picture in which the producer sends a message to write to a specific topic. The message is assigned to a partition by the partitioner where it is written prefixed with the schema ID. And then maybe there's a scenario in which some malicious producer wants to send schema IDs which don't exist, and for that scenario there's schema validation where there's an interface between the broker and the schema registry to check if the schema ID exists or otherwise reject the message. So if we sum all of this up, we find that schema registry has two main parts: a REST service for validating, storing, and retrieving the schemas in the supported formats, and serializers and deserializers that plug into Kafka clients to handle the schema storage and retrieval for Kafka messages across the supported formats. Let's see what the supported formats are. Confluent Schema Registry supports three formats: Avro, Protobuf, and JSON. And it supports, the support for these formats is not only in Schema Registry, but throughout the entire platform. And it's also possible to extend Schema Registry with custom schema formats as schema plugins, but we're looking here how to standardize, so that will not be part of this presentation. So maybe a little bit about the three formats. Avro has been developed as part of the Hadoop project, is the original default for Confluent platform, and it has the JSON-based representation and the binary serialization format. Protobuf has been developed by Google as a language and platform-neutral extensible mechanism for serializing structured data, and it has a custom structured text representation and the binary serialization format. And then finally, JSON schema is a declarative language to annotate and validate JSON documents, and it has both a JSON-based representation and serialization format. So that's great, right? But what do I need to use? What do I need to do to use them in my Kafka clients? So the first thing I need to do is connect my clients to Schema Registry. That means that I need at least a Schema Registry URL and perhaps also authentication to the Schema Registry. The schemas from the Schema Registry will be used in data serialization, and a schema defines the format of the serialized data and is used to validate the data as it is being deserialized by the clients. And when you write producers and consumers using the three supported formats, they handle the details of the wire format for you, so you don't have to worry about how they're being mapped to bytes. And here in this table, we have the relevant serializer and deserializer classes for producers and consumers of each data format. And depending on the chosen format, there will be different return types. So let's imagine a single topic with messages of multiple schema types with different data formats. What should a consumer consuming from this topic look like? Because there can be only a single deserializer configured per consumer. So then you're a little bit in trouble and you would have to use a more generic common type and then detect and handle at application level the more discrete type. And this already gives us a little bit a pointer that it's easier not to mix if you don't have to. So it's a good idea to use one of them, but which one? Let's explore further. So a serializer registers the schema in the schema registry under a subject name, and this defines a namespace in the registry. The compatibility checks are done per subject, and also the versions are tied to the subjects. So what happens when the schema evolves? The evolved schema will still be associated with the same subject, but it will get a new schema ID and a new version. And the name of the subject depends on the chosen subject naming strategy, for which there are 3 options. The default is the topic naming strategy, which derives the subject name from the topic name. The second one is the record name strategy, which uses the fully qualified record name as the subject format, and then the topic record name strategy, which uses the topic name followed by the fully qualified record name. So why do these strategies exist? What can they provide? The default naming strategy, the topic name strategy, names the schemas based on the topic name and implicitly requires all the messages in the same topic to conform to the same schema. The non-default naming strategies like record name strategy and topic record name strategy support schema management for use cases where grouping by topic isn't optimal. So a single topic can have records of multiple schemas. And this is useful when your data represents a time-ordered sequence of events and the messages have different data structure. And in this case, it is more useful to keep the messages together to be able to replay the chain of events regardless of their types. So here, a very obvious example is a financial service that tracks a customer account and might be initiating checking and savings, making a deposit, a withdrawal, getting approvals, and so on. So now, thinking back to our previous thought of using multiple data formats, we can see that even when using a single data format, then there can be variety based on events with different schemas. So we now know what our options in terms of data formats are and how the formats will be used. So now it is the right time to compare them to each other. But how to do that? What is important? One of the most important things is probably the programming language in your stack and that it has good support for whatever format you chose. 2 other important aspects are schema evolution and compatibility checks. So when using SERDES formats such as Avro, JSON schema, and protobuf, it is important to manage the schemas and consider how these schemas would evolve over time. Schema compatibility checking is implemented in Schema Registry by versioning every single schema, and the compatibility type determines how Schema Registry compares the new schema with the previous versions of a schema for a given subject. So when a schema is first created for a subject, it gets a unique ID and a version number, and when the schema gets updated, it gets a new unique ID and it's an incremented version number. There are 7 compatibility types, and they differ based on the changes which are allowed for a given subject. The default compatibility type in Schema Registry is backward compatibility, which means that consumers using the new schema can read the data produced with the last schema, but not necessarily with any schema before the last. So if my consumer should be able to read data using an even older schema than the one to last, then backward transitive compatibility can be used. Another important thing are schema references. It might be important to evaluate, is it possible to refer from one schema to another, or how fields are handled, does the presence or absence of fields have consequences for my clients, Is the order of fields maintained? Does it matter to the clients? And last but not least, there may be differences in the space requirements, and depending on the volume of data, this may be important. So let's look at the three data formats one by one. If we start with Avro, we can see, we can find the documentation page on the Avro Apache page, and it has excellent support for various programming languages and was designed with schema evolution in mind. On the right, there is a QR code to repository with very nice examples of compatibility tests in Avro. And we will use some examples from this repository to understand better how Avro compatibility works. So if we start with the very simple schema, which is shown here, we have a single field of type string called f1. We registered this schema to schema registry, and now we want to send a message to this data. And as long as my message uses the right schema, it is being successfully written to the topic. And that brings me to the thought, what happens if I add another field, right? I configured my schema to be backwards compatible. So I added my second field. And what do you think? Should this work? You're right, it doesn't. So for backward compatibility, it is allowed to remove fields or to add fields with an optional value. But since I did not supply one, my new schema is being rejected. So what do I need to do to fix this? I need to add a default value. So now with the new schema version, when I send a new message containing just the first field, the message is valid, and in the topic it appears with the first field as was present in my message, and with the default value of the second field, which was missing, but had the default in the schema. So what do I need to do if I want an optional field? In Avro, null is a type, and optional fields are composed by a union of null and the original type, and unions default to the first type in the union. So I still need to provide the field in the message unless I specify null as the default value in the schema. Here I can see the comparison between the first version of my schema without the default specified and the second version with the default. And this very short test gives us a feeling of what Avro looks like, how it works, what I need to think about when I do compatibility. And now we're going to have a look at protobuf and see how that compares. Protobuf also has great support for several programming languages, but the protobuf schema looks very different from the Avro schemas we've just seen. So looking at the sample protobuf schema on the right, a few things are worth highlighting. It has a very compact syntax, and interestingly enough, all the fields are assigned a numeric tag, and by default, all fields are optional, right? We've just seen several steps to add an optional field, and here they're all optional. We've also seen earlier in the presentation that a magic byte and the schema ID are prepended to the payload when using a schema. And in the case of protobuf, one more component is prepended, which contains the message indexes, where message indexes is an array of indexes that corresponds to the message type, which may be nested. So a single schema registry protobuf entry may contain multiple protobuf messages, some of which may have nested messages. And the role of the message indexes is to identify which protobuf message in the schema registry entry to use. If we look at a few simple examples, so using the schema from the previous slide in which 3 fields were defined, I want to check if fields are truly optional in protobuf. So I first send the message with all 3 fields, and the message is successfully written to my topic. And then I send the message with only the first 2 of the 3 fields, and now my message is still accepted, so I can confirm that the fields are optional by default. Similarly, I can evolve my schema to add another field and send messages with or without this additional field. Very straightforward. So what about JSON schema? JSON schema is supported by any language with JSON support and is a way to standardize and define expectations for the JSON data. In JSON, fields are also optional by default and the key is present or not. However, here we can specify required fields, but we cannot specify ordering, because in JSON ordering is arbitrary and there's no intrinsic way of ordering properties. The JSON schema compatibility rules are loosely based on similar rules for Avro. However, the rules for backward compatibility are more complex. So for object schemas, JSON schema supports open content models, closed content models, and partially open content models. An open content model allows any number of additional properties to appear in a JSON document without being specified in the JSON schema. This is achieved by specifying additional properties as true, and this is the default. A closed content model will cause an error to be signaled if a property appears in the JSON document that is not specified in the JSON schema. So here additional properties would be explicitly set to false. And then a partially open content model allows additional properties to appear in a JSON document without being named in the JSON schema, but the additional properties can be restricted to a particular type or have a particular name as specified in the pattern properties. So if we look at this in action, here's an example of an open schema. There are 2 fields in the schema and 3 fields in the message, and the message is valid with respect to the schema. And this is because the default of additional properties is true. When explicitly setting the value of additional properties to false, the message with the additional property is rejected as invalid. It is possible to evolve the schema with backward compatibility from having additional properties set to false to having it set to true, and then the message becomes valid, but it is not possible the other way around, as long as the compatibility is backward compatibility. So, a partially open content model allows additional properties to appear in the JSON document without being named in the JSON schema, but they can be restricted to be of a particular type or a particular name. And this is achieved by specifying a schema for additional properties or a value for pattern properties that maps regular expressions to schemas. I can evolve my previous schema to include pattern properties so that I allow additional properties of type string whose name starts with, for example, here S. So we've seen a few very basic examples which have shown us how different the different formats are, especially for a centralized team which doesn't necessarily focus on formats. So let's try to sum our findings up. All of the 3 formats support various programming languages. They have different representations, and while they all do support schema evolution, the way in which they do this is very, very different. We have seen that protobuf is very compact and JSON schema very verbose, and each format has advantages and disadvantages, and we can't help but conclude that there is no right format, and you have to pick the one you're most comfortable with or that fits the workload or your ecosystem. But even though we didn't find that one is more valuable than the other, we realized the amount of complexity which can come from mixing them, especially when looking to standardize at a large scale. So I would like to conclude my presentation with a summary of what Schema Registry is, that it's an add-on to the Kafka ecosystem, which allows clients to know and handle the evolution of data and supports 3 serialization formats, and with a recommendation to use a consistent organization-wide enterprise data governance strategy and not mix data formats within the same topic at all. And if needed, different formats can be applied to different topics, but do consider whether the advantages of doing so outweigh the valid complexity. And I guess I wouldn't be a solution engineer if I wouldn't end my presentation with a link to a training. So on the right is a link to a course on the Confluent developer website, which includes additional recommendation on how to master production data systems, including to try to standardize on one data format. So I hope you found the presentation useful, and I'm happy to answer any questions you may have.